Hello friends, in today's class we are going to talk about round robin scheduling. Welcome here, and now we are talking about round robin scheduling, which is used in a time shared system. Okay, time shared system. And I have already described in the previous lecture what exactly is the time sharing systems, where multiple users are there, and each user may feel that the system is dedicated to them. So that is the first point, that round robin scheduling algorithm is designed especially for the time sharing systems, and this is not nothing new about new policy. It is FCFS scheduling. So they will be scheduled in the order of first come first serve basis. But the only idea here in this case is preemption is added to enable switch between the process, right? And what will happen is each process will be allocated a given CPU in a fair share system. Okay, so now they will be they cannot say that someone is starving or being blocked for the longer period of time. And how long this process is going to run in the system, that will be defined by the small unit of time that is called the time quantum, or the time slice is defined. Okay, so we are going to have a fair that round robin, and that everything will goes, and then again the second round will start and every process will pass through. The time quantum is generally 10 to 100 millisecond in length, and its mode is preemptive. Yes, it is in preemption mode. The ready queue is, I already told you that how exactly the ready queue will look like, and it is treated as a circular queue, and the CPU scheduler goes around the ready queue, allocating the CPU for each process for the time interval of up to one time quantum. Okay, and one time quantum is what? That is the smallest unit of the time that they're going to share. Now let's implement this, and let's see that how does and it is the question here in this case, just calculate the average waiting time. So now P1 is there, and we are going to allocate P1 for the first time, and time quantum is 4. So 0 to 4 it will be allocated, P1 will be allocated. Let's have Gantt chart for this. Okay, so now P1 is allocated with this 4, and then we will come to what? After 4 time unit, we will come to P2, sorry, which will run for 3 time unit because the burst time is lesser than this, and it will be completed by 7. Then again we'll go to P3, and that will again terminated by 10, and then we are left with this P1, P1, P1. So that will be 14, 18, 22, P1, P1. So now already it has a run for the 4 time unit over here, and then I required 26, and this is 30. Okay, so that is a round robin scheduling algorithm. And if you talk about the waiting time, okay, waiting time. So now a few more times I can calculate is the completion time, say T. What is the completion time? Completion time here in this case is 30. Okay, let me write here CT 30 and 7 and 10. Nothing is mentioned about the arrival time, so I assume that all are arrived at zero instance. And if you can say the waiting time, how long they have been waited. So okay, so turnaround time is what? Turnaround time is turnaround time here is completion time minus arrival time. So turnaround time will be also 30. Okay, let me write here turnaround time will be what? Here in this case will be 30, and it will be 7, and it will be 10. Correct? So now why? Because we don't have an arrival time, and now we can say the waiting time. Okay, the waiting time is okay, we have a completion time, turnaround time, and now Okay, now 30 minus burst time, 30 minus burst time. So 30 minus burst time is 30 minus 24, which is 6. And 7 minus burst time 3, and that is 4. And 10 minus 3 is 7. And average is 17. Average, we are asking average waiting time. So average waiting time will be 6 plus 4 plus 7 divided by 3, and that is 17 divided by 3, and that will be 5.15 to 66, let's say 7, 5.667, it's a millisecond. Okay, so that is the round robin scheduling, and that is the average waiting time. I hope you agree with this solution. Now, if there are n processes in the ready queue and with the time quantum q, then each process will get 1 by nth of the CPU time in the chunk of at most q time unit, right? So, right. So, if there is a, like here, if there are n processes in the ready queue and the time quantum is k, each process will get 1 by nth of the CPU time in chunk of at most q time unit, right? So 1 by nth time, definitely they are going to, suppose there are 4 processes are there, let's say P1, P2, P3 and P4, right? And suppose this is the with the time quantum q, 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 q. So each process will get how much time? 1 by nth at the chunk of what? Q. So it is saying that each process, like suppose this is the complete time. So each process will get 1 by 4th of the CPU time in the chunk of what? In the chunk of Q. Then this is the chunk of Q. Each process must wait no longer than n minus 1 Q time until the next time quantum. Okay, so now here if I say again P1, right? After this, if I get again P1, how long P1 waited? So it has waited this chunk, and this chunk. So 3 q times it waited, and that it is saying n minus 1 into q time until it get the next time quantum. This is at most. If some process exit in the middle, then this will be even lesser than this. For example, 5 process and a time quantum of 20 millisecond. Each process will get 20 millisecond in every 100 millisecond. Okay, so for example, there are 5 processes of the time quantum of 20 millisecond. Each process will get 20 millisecond of every 100 millisecond. Yes, that is also true that out of this, let's say here, if I consider 4 processes, out of this 80 millisecond, 20 millisecond will be for P1, and that is what is saying that out of this 100 millisecond, 20 millisecond will be for this each process will get. Now, how long should be your time quantum? Okay, so what should be the duration? How long? Time quantum should be, right? This is very critical question, and can it be very small? Can it be very large? Right? Now, if the time quantum is very small, then in that case, CPU efficiency will degrade. Why? Reason being is if you have a too small time quantum, then there will be more context switching, and context switch time, right? Context switch time will be more. Okay, and more context switching, but it improves the response time, but there will be large number of overhead. If it is large, then the context switching is still an overhead, but there will be less response time. If it is very large, okay, then it is work like an FCFS approach, right? And very poor response time. So our whole purpose of this response time will be lost. And that is the main reason that we started with this time sharing scheduling policy. Okay, so we have to be reasonably good with our time quantum. It should not be very small, and it should not be very large. Otherwise, it will behave like a FCFS. Turnaround time is the summation time, right? It is the arrival time or summation time. Arrival time. Okay, completion time minus arrival time. Okay, and this is the time quantum, different values, and this is the average turnaround time, and they have been taken a graph for the different time quantum value. Okay, so like here in this case, if it is a one time quantum, then this is average is around 11. For 2 it becomes 11.5, larger turnaround time. For 3 it becomes around lesser value, and that is somewhat around 11 point, let's say 10.7 or 8. For 4 it is slightly increased, 11.5. For 5 time quantum turnaround time increases most, right? And for 6 again it is coming down to 10.5, and 7 it is being constant. So we can say that this is the best 6 is the best performance of it. Turnaround time also depends on the size of time quantum. As we can see in the figure, average turnaround time of a set of processes does not necessarily improve as the time quantum increases. Okay, so it is not mandatory that you increase the time quantum and it will average turnaround time will increase. In general, the average turnaround time can improve most of the process finishes their next CPU burst in a single time quantum. Okay, in general, average turnaround time can be improved if most of the process finish their next CPU burst in the single time quantum cycle. Okay, so that is very trickier, and it is not always true. Now, this is the last problem that I'm leaving you here with your homework problem, and let's assume here that the time quantum is 2. Okay, so with time quantum 2, complete this Gantt chart for this particular problem. Okay, so that's all for this round robin scheduling algorithm. The next topic that we are going to learn is multi-level queue scheduling. Okay, so that's all over here. Thank you.